In this session, we'll understand the effect of variation of load in case of synchronous motors as well as in case of synchronous generators. Uh, as far as synchronous generators are concerned, in, in power plants, we use a number of synchronous generators in parallel uh, for operation. The voltage level is very high. The frequency is set to 50 Hz. So we consider it as an infinite bus where irrespective of the load variation, the voltage and frequency levels do not change. So that's for a set of parallel synchronous generators. But in case of a single synchronous generator, if you are using a synchronous generator in a standalone mode, what effect does the load have on the synchronous generator's operation? We know by increasing the load, the real or the reactive power demand will increase from the generator with the increase in reactive power demand. That will actually mean the armature current, the load current drawn from the generator, will also increase. But the field circuitry has not been changed. That's why the field current is constant. Therefore, flux is constant. So what we are saying here is that the armature current is increasing, but field current field current is same. That means uh, and the prime mover is also moving at the same speed. It does not depend on uh, the rotation of the rotor. It does not depend on the irrespective of whatever load we are putting on the electrical load we are putting on the synchronous generator. The speed of the synchronous generator will not be directly affected. So the generated voltage, that is EA, we know EA is nothing but proportional to phi and omega, that's flux and speed. So this will remain more or less constant. But due to increased load, IA has increased. And we know that for a synchronous generator, EA is, or we can write the terminal voltage. The terminal voltage is the generated voltage minus mm, J times IAXS. We are assuming as a condition where we are assuming for a negligible armature resistance. So since IA has increased, EA remains constant. VT therefore decreases as the load on the synchronous generator is increased. Uh, this is a normal understanding of how VT will change. The more clear perspective can be used drawn from the phasor diagram. Let's see what the phasor diagram gives us the information about the change in voltage with respect to increase in the load. Let's assume first for a lagging case, this is Vt initially, this is Ia. That means J times Ia axis will be somewhere along this direction. J times I axis will be parallel to this line. That is, this will be J times XSIA. So that means this is EA. Now we are saying that we are increasing the load. Increased load means increased armature current. So as we increase the load, if this is IA, this is IA dash now. IA dash corresponds to increase in load, uh, increased condition of load. Uh, we'll not be drawing VT, we'll actually be deriving the VT. We know that with increased load, what will happen is that VT will decrease the terminal voltage VT dash. That means now J times IA access will be somewhere here. J times IA access will also increase. If we take this as a center and we draw some line here, we will have this, it will be EA dash now, where EA dash and EA, the magnitude of these two will be same as we have drawn a circular path here. The radius will be same, so EA and EA dash will be same. IA has increased, J times excess IA has increased. So what we are seeing here is that VT dash will have to decrease for maintaining EA and increasing IA. Fine. So this is a case of a lagging load. For a unity power factor, what we see is if this is VT, in this case IA will be in this direction. Uh, Accordingly, J times IA access will be somewhere here, and this will be EA. Now as we increase load, EA has to remain constant. That means new EA dash will be along a semicircular path with this as the center. IA will increase. Since IA has increased, we can see that J times IA axis will be somewhere here. So if this is the origin point of J times IA axis, that means VT dash will be somewhere at this point. So this is a case of a unity power factor. We are again seeing that there is a decrease in VT. Now for a leading load, this is VT, this is IA. That means if we have J times I axis in this direction, that means J times I axis will be somewhere around here. That means EA will be somewhere at this point. Now using a semicircular path, now using a circle, now we are increasing IA. That means IA dash will be here now. Using a circular path, we can see that EA dash will be somewhere at this point now. If EA dash is at now this point, that means J times I axis has to be somewhere at this point. That means this is the point from which J times I axis originates. That means VT dash is here. So in case of a lagging load, when we are applying a lagging load, the power demand increases, the current increases, uh, while maintaining the same induced EMF. We can see that VT, that is the terminal voltage available to us, decreases. Same happens in case of a unity power factor. Here the decrease is more significant. Here the decrease is less. That's the difference between the lagging load and a unity power factor load. But in case of a leading load, what we are seeing is that the terminal voltage increases. This is because, as also already explained in the previous session as well, that we that at leading load, synchronous generators will start actually becoming a supply of reactive power. So for a lagging load, the terminal voltage will decrease significantly. For a unity power factor load, the terminal voltage will decrease slightly. For a leading load, the terminal voltage will rise. So, if we go by intuition, we would not expect the load. We would not be expecting a voltage to rise as we increase the load. So, the natural load will actually determine the voltage at the uh, terminals. That's the voltage available uh, to the consumers. So, for a capacitive load, there will be actually a rise in voltage level at the consumer end or at the terminals of the synchronous generator. Now, as I said to you, now in case of a power system or a power plant, mm, there are a number of synchronous generators operating in parallel. So this does not arise there. This the voltage and frequency of the generator will be more or less constant. Uh, the effect of load variation in synchronous motors needs to be seen as well. Uh, Again, if a load is attached uh, to the synchronous motor, we need to see. In yesterday's case, we changed the field current and we assumed that the real power demand was same. Here we'll be assuming now, since the load is varying, field current we are not bothered with the field current. The real power demand will change here. That EA sin delta and IA cos theta that we had kept constant for the operation of field current. Uh, in case in when we derive the V curve of the synchronous motor, that will no longer be the case here. Simply, what will happen because of the variation of load needs to be seen is that there will be an increase in the demand of current. So this is the terminal voltage. Now this terminal voltage is actually the voltage that we are applying in case of a synchronous motor. So this cannot change in case of a synchronous motor. In case of a synchronous generator, the induced EMF, that's EA, cannot change, and in case of a synchronous motor, VT cannot change. So let us assume that initially the motor is operating at a leading power factor at a leading load. That means IA is in this direction. Uh, this will be J times XSIA. That means EA1 will be somewhere around here. If this is IA1, initially the current drawn at a certain load is IA1. J times XS IA will be in this direction. Now, since this is a motor, here equation of VT and EA in case of a synchronous generator, the governing equation is Vt is Ea minus J times Ixs. But in case of synchronous motors, Vt is equal to Ea plus J times Ixs. So that's why J times Ixs is coming in this direction here. We are drawing it along this direction. So this will be Ea1 uh, for this case. So here the real power is changing. We are not changing the field current. Since field current is not changing, Ea will not change. Ea will remain constant. So using this line, we'll have to draw a semicircle. So corresponding to mm, yeah, these equations of power. This is angle theta. This is angle delta. So now in this case, EA is constant, VT is constant, XS is constant. So sine delta has to change so that P will change. That means actually the angle delta has to change. And accordingly here root 3 VT is constant. IA is no longer constant. As we increase the power, the current demand will also increase. Simultaneously, cos theta can also change for accounting for the increased power demand. So what we'll see in case of a synchronous motor is once we increase the load, the real power demand has increased. That means delta has to increase so that sine delta increases so that P increases. So this will be in the new EA2 where EA1 and EA2 the magnitude of these will be same, but delta has changed from delta 1 to delta 2 such that sine delta change such that P increases. That also means that IA has to increase in such a fashion uh, like this. The angle theta has to decrease for cos theta to increase. So IA2 here has increased, the armature current has increased, but simultaneously theta will also change, cos theta will also change as the power changes. With further increase, we'll see that EA3 will be somewhere around here. We have now delta 3 and we'll have IA3 somewhere around here. IA3 will be greater than IA2 and this will continue. We'll increase IA4. So once this keeps on increasing, we'll see that IA will now shift into the lagging power factor region. It will touch the unity power factor region at one point and then it will go into the lagging power factor region. So this here shows how IA is varying. IA is increasing with increased real power demand. Uh, the real power demand is increasing, and accordingly we can see that EA1, EA2, EA3, EA4 they remain same. The induced EMF is not changing because we are not concerned here with the field circuitry. The terminal voltage is not changing, delta is changing, theta is changing. So we can see in case of the increased load, uh, what happens is that the system moves from a leading power factor region to a lagging power factor region. Therefore, the so and load increase here will actually mean uh, if it was already a lagging load, it would have made it only more lagging. But it for the leading load, load irrespective of whether the nature of the load, uh, we are assuming actually a balanced load here. What happens is that the motor will the synchronous motor will start operating from a leading power factor region to a unity power factor region, then to a lagging power factor region. So this is about the load variations on synchronous machines. Now one last topic we'll need to see is how to operate the synchronous, what conditions to keep in mind while operating the synchronous generators in parallel. As I said to you that the load demand of a synchronous of a power plant is very high. A we cannot use a single generator to actually make uh, to supply the to supply a number of systems. So we'll have a number of systems actually be operating in parallel. Uh, so what happens is generators will be operated in parallel. Uh, the frequency and the terminal voltage here will be mm, constrained by the infinite bus. That means the terminal voltage and the frequency will be nearly constant. So when we uh, connect one generator with another generator, uh, the net result is that the real power of one generator plus the real power of another generator just sums up. The total power will be the real power supplied by one generator, the real power supplied by another generator. Similarly, the reactive power will be uh, Q1 plus Q2. So, what conditions we need to keep in mind while operating the generators in parallel is one, phase sequence of the machines. By phase sequence, we mean that if the phase sequence of synchronous generator is ABC, the phase sequence of synchronous generator 2 should also be ABC. That is, A should be and be at an angle of 0 degrees, B should be at an angle of 120 degrees, and C should be at an angle of 240 degrees. It cannot be one is at ABC and another one is at ACB. This will not work. The RMS line voltage of the bus bar or of the machine that will be incorporating in parallel with already running RMS voltage of incoming synchronous machine that we are actually putting in parallel with another machine should match the bus bar voltage or bus bar or the synchronous machine that's already available there should meet the should have the same RMS voltage. Phase angles should be same. We cannot have one synchronous machine at a phase of 30 degrees and another one at a phase of 45 degrees. And the frequency, the phase angle means both should be. This is very important to make sure that both the machines are actually synchronized together. Frequency of the two should also be nearly same. If one is operating at 50 hertz, another one is operating at 49.95 hertz, so that's okay. We cannot have one is operating at 50 hertz and another one is operating at 40 hertz. That's not uh, how this works. So this is actually how these are the necessary conditions that we need to keep in mind while operating uh, the synchronous generators in parallel. If the synchronous generators are not made work in parallel in this fashion, they will go out of synchronization and there will be a loss of synchronization. So the advantage of this operation is that it will have higher voltage levels will be available, higher power levels will be available. We can increase the load on the system. We can actually make sure that if the system is lightly loaded, one alternator can be shut down while the other can operate it at its full load. So this high efficiency of the system is increased, the operating cost as such is also reduced, and it also makes sure that the protection of the system is better. So this is about synchronous machines and synchronous generators. With this, we wrap up the synchronous generators, synchronous machines. Uh, with this, we actually wrap up the electrical machines course.